So, okay, let's start. Today, for this lecture, we're going to introduce something very important for you guys. Today, we're going to introduce the spin-orbit interaction. The spin-orbit interaction to explain the following. So basically, we got from our harmonic oscillator that we got equidistant energies, right, between different oscillator quanta, n equal 0, n equal 1, n equal 2, n equal 3, and so on and so forth. And this leads, if we have the building, our building for protons or for neutrons, as the binding goes down, for us to remember, the neutrons will be the building will be very similar, but for the neutrons, we have a deeper potential. Remember that this is all in a potential, right? In the harmonic oscillator, as we always say, this building, it will look very similar for neutrons because of the Coulomb repulsion. The protons will be less bound than the neutrons, but the buildings will look almost exactly the same, but ones will be a little bit deeper than the other one. So we say that the occupancy of these fellows is 2, right? The same for these fellows, 2, and we have the magic number 2. Then for this guy, we say we have 1, 2, 3, 4, 5, 6, and we got 6 plus 2, a magic number of 8. The same thing here, 1, 2, 3, 4, 5, 6. 8. The next one, we have 12 here, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and the same thing here. As many, these are as many as we can have on this flow, 12, but we don't need to fill the flow. Some nuclei, obviously, we have less proton and less neutrons here. They don't need to fill it up. So only when it is full, the whole floor, we cannot take any more because of the Pauli principle, right? We cannot have more because then the quantum numbers will be the same. So we have as many as the Pauli principle allows. And then you have here a magic number, which is the 20. But then if we go to the M4, and we do our table as we did here the other day. If we do our table right here, right? For the 4, we have the 1p and the 16, which makes 20. So 20 plus 20 will give us 40. What is now the cursor here? 40, right? So the same thing, 20 here and 40 here. So remember always these energy gaps are the reason these large energies or energy gaps are the reason for us to have a stable nuclei. So as I mentioned yesterday, 40 is not a magic number, and the harmonic oscillator starts failing, right? So the harmonic oscillator starts failing for this particular nuclei because 40 is not a magic nucleus. We mentioned that 8 and 8 corresponds to oxygen 16, 2 and 2 corresponds to helium 4, 20 and 20 corresponds to calcium 40. But 40 and 40 is not a magic nucleus. That will correspond to let's look at the charts of nuclei. Let me just go here. And let's go to documents and then acro read chart of nuclei. And then here we got the 30. Let's go to the 40. And then 40 zirconium, I think. 40 zirconium, and zirconium 80 is here, which is very unstable. And actually, this is not a magic nucleus. This is not a stable nucleus. These fellows are more stable. Calcium 40, as you can see, is actually down here, but it's nicely stable. But as you can see, krypton 40 or zirconium 40, sorry, is not is very exotic, and basically the harmonic oscillator fails to reproduce the next magic number, which is actually 28. Next magic number here will be 28. So how do we do this in a way that we can reproduce these magic numbers? And this was the idea of the harmonic oscillator. Basically, we have a potential, which is actually, yeah, it's going to be minus L dot S, right? And according to L, which is the orbital angular momentum, and S, which is the spin, we are going to see what happens to these levels once we apply a perturbation. And so far, we haven't applied perturbation theory. You haven't done this in quantum mechanics. But perturbation theory is something very relevant in physics in general. And I am of the opinion that I should mention it a little bit for this particular case, which is the simplest case scenario. We are going to deduce the energies. So this is going to be the case. So we have a level, let's say the n equals 0. Or let's call it the 0s, right? Where this is characterized by our wave function and our energy, 3/2 of h bar omega naught. And this is the main physics. The main physics is h, the Hamiltonian, is given by h naught, which is our harmonic oscillator. And this is going to be perturbed by a physics, by another Hamiltonian, which has a much smaller effect than h naught, right? But it's an effect, which is a subtle effect, but it will provide the difference that we're looking for here. So let's apply this and see how this basically change, this level change once we apply the Hamiltonian h prime. So basically this will be h naught, and it will be h naught plus h prime. Say whether this goes up there, whatever it comes down, you know, it will change the energy in a way that it will, as we shall see, incorporate the magic numbers beautifully. So this spin orbit interaction is key to understand the shell model. So let's do some calculations now. So let's see. To include the spin orbit interaction, we had to include the total angular momentum J, which is equal to L plus minus S, as you know, where S is always equal to 1/2. So in this case, we need to figure out what is the spin orbit interaction, right? And this is a negative sign here. And we are going to do the following. J square is going to be equal to L square plus S square plus 2LS. And from here, we're going to deduce that LS is equal to J square minus L square minus S square divided by 2. And now, this energy, according to perturbation theory, the perturbed energy will come as delta E, that will be the change in the energy, will be equal to NLJ MJ LS NLJ MJ, which these are L square, actually J square, there's also an S here, and an S here, S square. And as we know, from make it small j's, because that's we are talking about the small j's right now. So we're talking about single particles, so small j's. So these all are these are all small l, small j, small s. So as we know from quantum mechanics, j square applying on jm, let's call it jm to simplify things, is equal to h square j plus 1 jm. So these are general rules which apply to everything. L square over Lm is equal the same thing. H square L plus 1 Lm, right? So, but as I say, I'm using these bases in particular, N, L, S, J, and Mj. And this is very important to be able to apply perturbation theory, because all these operators, L, S square, and J square, they commute with LS. So basically, we can have a LS equal to 0, right? And S square LS equal to 0, and J square. So basically, we can have a set of independent operators, and we can have our basis states, which are composed on those wave functions, which are defined by now J, oh, let's call it like this, NLJ or LJMJ. We could have used a different set of operators, but another set, for instance, we could have used NL, ML, S, MS, you know. But then here we see that L set LS is different of 0. And these are the things that I would like you to calculate to apply quantum mechanics, because with this, without the fact that the basis states, the operators which conform the basis states, the fact that they commute with LS, with the perturbation Hamiltonian, right? This is our H prime. Without this fact, we cannot apply perturbation theory. We cannot apply the fact that the change in the energy will be given by this equation here. So now let's apply the equation. And let's say, okay, what is LS applied on NLJ, let's forget this fellow, NLSJ MJ. So here we're going to introduce that LS, we just deduced it before, is equal to J square minus L square minus S square divided by 2, right? So, and the fact that J square on J, let's call it JMJ, is equal to H bar square J plus 1. This comes from quantum mechanics, JMJ. And the same applies for L the same for any angular momentum. So basically, we are going to have here, let's do it one by one, that j square, okay, let's put these guys here, 1/2 of j square minus l square minus s square applied onto NLS JMJ. This is going to be equal to 1/2 of j, actually let's put the h bar square here, j plus 1 minus l plus 1 minus s plus 1. But as we know, s is equal to 1/2. So that will be 1/2 plus 1, 3/2, 1/2. This will be 3/4. This whole thing will be 3/4. Okay. So now we have an equation. We applied our perturbation, and basically this perturbation will lead to this 1/2 of h bar square j plus 1 minus l plus 1 minus 3/4. And now we know that j can be either l plus minus 1/2, right? So basically, we are going to have two possibilities. J, let's go here, j equal to l plus 1/2, and then this will be equal to 1/2 of h bar square, l plus 1/2, l plus 1/2 plus 1 plus 3/2, minus l plus 1 minus 3/4. Right, and these all close here, these brackets. And now let's see, also this is a bracket here, so that will be 1/2 of h bar square. So that will be l square plus 3/2 of l plus 1/2 of l plus 3/4 minus l square minus l minus 3/4. And this will be l square here. It will cancel with this l square. We have 2l here, right? Minus l. This 3/4 will cancel with this minus 3/4. And then we remain with 2l minus l. So basically, we have l h bar square over 2. If I'm not mistaken. You see? 3l plus l, 2l minus l. Right. So then the second possibility will be j equal l minus 1/2. Right. And then this, we are going to apply the same thing. Basically, this is our general formula here. And well, we can calculate it. You can do the same thing, but let's calculate it because I don't know what is the result of my head. So let's calculate it quickly. So we have j l plus 1/2. So we have that for j equal l plus 1/2. We have that ls, right, is equal to actually ls, not ls, but this is not it properly. Ls applied onto, so these are operators that need to be applied onto a NLS JMJ. And this is equal to L h bar square over 2. L h bar square over 2. So now if we assume that J is equal to L minus 1/2, then we have that this thing, LS and LS JMJ will be equal to h bar square over 2, right? That's always there. And now we have that J plus 1. What is my cursor here? Here it is. So J will be L minus 1/2. J plus 1 will be L minus 1/2 plus 1, right? Which is plus 1/2. Let me see. J plus 1. So this will be plus here minus L plus 1 minus 3/4. And this will lead to, this will yield h bar square over 2 L square plus L half minus L half minus 1/4 minus L square minus L minus 3/4. See? So then this will be h bar square over 2. So again, L square cancel with this L square. This guy cancel with this guy. So we will have minus, actually, minus 1/4 minus 3/4 is 1, minus 1, minus L. So that will be L plus 1, right? So as the potential is given minus Ls, right? So if, let's say L is equal to 0, so there will be only J equal to 1/2. So basically, we only have the situation where for L equal to 0, here we have it, this actually, and then now let's change this color just for us. This will be 0 for L equal to 0, the contribution from the spin orbit interaction. But let's actually first go back and determine finally the, let's go back here and let's close the calculation that we are doing right now. So now we have that this, we are always missing the NL SJMJ. But remember that delta E, the change in the energy from the unperturbed energy, is going to be equal to NL SJMJ V, I mean LS minus LS, which is our perturbation, NLSJMJ. And this give us two possibilities. And let's see now for, say, for S equal to 0, which is L equal to 0. So we have only the top possibility, L equal to 0 here. So J is equal 1/2. So our state from the harmonic oscillator doesn't change anything at all. So this will be the 0S. So for L equal to 0, there's no change in the energy. So delta E is equal to 0, right? Because at the end, this energy here is equal to L h bar square over 2. For the case of L equal to 0, we only have J equal to 1/2. Okay, so now we can apply this, and let's apply it to P. Let's apply here to the 0P and see what happens. So for the 0P, we will have P is equal to 1, right? So then there will be a change. there will be a delta E. There will be a change which will be given here by 0p 3/2, which will be 1 plus 1/2. Remember that there's a negative sign here. So then this guy will come down by a difference given by L h bar square over 2, where L is equal to 1, right? And there will be a going up here, which in this particular case will be minus plus h bar square 1 plus 1 2. So basically there will be a increase of h bar square. So for the 0p 1/2. So you see the p 3/2 comes down, and this is the j, and this is j here, 1/2.
Excuse me, Prof. I think you're not sharing.
No, I'm sharing. So, okay, can you see guys? Can you see?
Yes, Prof.
I'm
I can
sharing.
see your screen.
Yeah. So okay, let's summarize this because this is quite complicated. Again, we have done lots of calculations, but we need to explain things, right? So let's so basically we have let me summarize this. We have applied perturbation theory in a very very fast,
Prof. Nico?
and we have, tell me.
Prof. Nico?
Yeah.
What is the perturbation theory? What is that about?
So perturbation theory is our physics here. We have described the physics by the harmonic oscillator, right? This is the physics of the harmonic oscillator, which is basically a potential which looks like this, right? And all these levels are in that potential. However, we realized one thing, that the 2, 8, 20, the next one comes 40. So this was wrong. The sequence of states, or the sequence of magic numbers, these are called the magic numbers, right? Was wrong. And this nucleus in particular, the 40, is not a magic number. And these nuclei with that particular number, they're not particularly stable, right? So then what we need to do is to apply a perturbation. So the perturbation will come the harmonic oscillator plus a perturbation. Okay. So that perturbation will affect these levels in a way that we are calculating right now. So this basically, the total Hamiltonian will be h naught plus lambda h prime. So we will have this guy is still the harmonic oscillator, and this guy is our perturbation, which we are calling Ls. Okay. So this perturbation will affect the levels that we are exploring right here. As we can see, for the 0s now has become the 0s 1/2. And now this is a new labeling, which we are going to call J, the total angular momentum. But for the 0p, suddenly these guys have changed. And now this 0p has split into two. The 0p 3/2, which corresponds to J equal L plus 1/2, and the 0p 1/2, which corresponds to J equal L minus 1/2. So we have the applied perturbation theory in a way that this new change in energy, this delta E, right? This delta E, what I'm talking about is the energy difference between the original harmonic oscillator and the difference of these guys going up and going down. So there's an increment in energy, which depends on J, L, whether L is L plus 1/2 or J is equal to L minus 1/2. So this change in energy basically is going to have the energy of the Hamiltonian is going to be the energy of the harmonic oscillator, which we know for the ground state was 3/2 of h bar omega naught, plus this increment in energy that we are determining right now. So the 3/2 h bar in omega naught, it will change in energy or not. For this particular case, for s equal to 0, for 0s, this doesn't change in energy, as we have just demonstrated before, because the energy will be for J equal L plus 1/2. We determine here was given by L h bar square over 2. So this delta energy is going to be, the increment is going to be, again, I lost the, so what was it? I forgot now. L h bar square over 2. L h bar square over 2. And for J equal L minus 1/2, we also calculated it right now, and it was minus h bar square over 2 L plus 1. Oops. So this was minus h bar square over 2 L plus 1. With the difference that actually the perturbation was actually minus Ls. So basically the J with the larger number will come down, and this is what happens with the 0p. With the 0p, this guy will come down by a factor of so this will be up positive and this will be negative. So this is the other way around in the so this guy will come the J plus plus 1/2, which is the 0, basically the 0p 3/2. This is for J equal L plus 1/2. It will come with a delta E of minus L h bar square. So this difference here will be of minus L h bar square over 2, which in this case L is equal to 1, right? For the particular case of P, for the 0p, this will be equal to 1. So basically this delta E will be minus h bar square over 2, right? Delta E with respect to the 3/2, I mean now it is 5/2, right? The 5/2 h bar omega naught. And now there will be another increment here, and this increment will be the plus 1 here, 1, 2. Basically, there will be an increment of h bar square. So the new 0p, it will look like this. Now let's draw the sequence. Here we go. Here, actually, I draw it here. We could zoom in there and see that now one level has been created. Let's zoom a little bit. So one level has been split onto 2. So the 0p in particular has, now we need a new quantum number to describe it, the 3/2, and the 0p 1/2, where these are the energy, the 5/2 h bar omega naught has been shifted in energy by the perturbation, by the spin orbit interaction, by a factor which is minus h bar square over 2. And this has gone up in energy by a factor which it is h bar square. And this is what we have calculated in a way that if we go back to the original slide I wanted to here in a way that suddenly we have split the levels. Here actually it is nicely represented in this one here, this one, the share model. Here actually, where at the beginning of the chapter we saw how the splitting or the spin orbit interaction, spin orbit potential, actually splits in a way where the 40 suddenly is 28, and the next one is 50, the next one is 82, and so with the spin orbit interaction we can reproduce finally all these magic numbers, all these energy gaps, these large energy gaps, which makes those nuclei which have fill up this last flow, because the next one is far away in energy, make this particular nuclei extremely stable compared to others. So basically, I mean, I can repeat but everything is in this calculation. So Shoki, is that clear? So Getso, how do you see things?
Yes, so I wanted to ask, so the reason we add the perturbation is so that we can be able to get the magic numbers.
Correct. So
Okay.
the physics that we have originally wasn't enough, right? The physics of the harmonic oscillator wasn't enough. So for that we needed to make the harmonic oscillator. We needed to add, this was the harmonic oscillator, let's say H naught harmonic oscillator, and this was an energy for the ground state of 3/2 h bar omega naught. This was the 0s. As we see the spin orbit interaction, we apply the H naught plus, no, actually minus the spin orbit interaction. But let's call it plus the spin orbit interaction, and nothing changed for the 0s. However, the 0s has now changed, has to be defined as with a new quantum number, which is J, which is L, in this case, plus 1/2, because you're going to have a negative quantum number. So L equal to 0. So the next one was the 0p. And we have seen that there's a little change in energy. And we see that the lower J, I mean, the higher J comes down in energy. And this corresponds to, and the first one's to J L plus 1/2. The next one corresponds to J equal L minus 1/2. Well, L in this case is equal to 1, right? Because P, remember, S, P, D, F, G, F, I mean, I. So this is L, right? And this is 0, 1, 2, 3, 4, and so on and so forth, right? So now we go to the next one. We can go to the, and this is very interesting. I want you to calculate as an assignment. So these guys were 0D and 1S. As we know, the 1S, nothing is going to change because again is L equal to 0. So the 1S will remain there, but the 0D will split again into 0D 5/2 and a higher energy here, which will be the 0D 3/2. And then again, this guy which was 40, right, and didn't work out the sorry, so it was 2, 8 was 20, sorry. This was 20, and this was 8, and this was 2. Still will remain the same magic numbers, 2, 8, 20. But now these guys, which are going to be the 0F, SPDF, and the 1P, actually they will come there, These guys, which are degenerate, we also split in a way that the next gap will be at 28, and the magic number will be reproduced nicely by the addition of the spin orbit interaction, by adding LS. Right.